Greenhouse gas is really the fundamental starting point for most of life. The problem is we're putting too much of it into the air. Well, nature has this really interesting philosophy, and that is that there is something of value in everything. And that's the basic premise of nature. CO2 as an example. As you mentioned, nature eats CO2. It's valuable. Methane's the same thing. Whatever it is, nature will find a way to turn it into something useful. And it turns out that you can feed methane or carbon dioxide to a microorganism, a natural microorganism. It'll eat that as a food source, and part of what it'll make inside of its cell is PHB. So here you have a naturally occurring process versus a synthetic process. The reason why that's so important is because when that synthetic material ends up in nature, nature doesn't know what to do with it. It doesn't have the tools and the resources to break it down like a food source, like it would with a banana peel. In contrast, PHB, it does have those tools.
Welcome to Mindful Businesses, presented by Sarani, and I'm your host, Vidya Iyer. In our podcast, we bring to you brands that are mindful in their practices and processes. A mindful business adopts and employs sustainable social, economic, and environmental practices. Today we have with us Mark Herrema, CEO and founder of Newlight Technologies, from greenhouse gases to regenerative materials. So he joins us from Los Angeles, California. Welcome, Mark.
Hi, Vidya. Good to be here.
Recently, more than ever before, there has been increased awareness of the negative impact of greenhouse gases. What are the most prominent greenhouse gases? There are several, right? Which are the most prominent ones in our atmosphere?
Well, I'd say the two most talked about greenhouse gases are carbon dioxide and methane. And those two gases are the gases that humans are contributing more and more to emitting into the air and are causing the warming that we're seeing globally.
What percent of carbon dioxide is there in the atmosphere right now?
So the atmospheric concentration of carbon dioxide is around 400 parts per million. So that may seem relatively low, but because it's a heat-trapping gas, even low amounts of this gas in the air will cause the air to heat up.
Greenhouse gases have existed in our planet forever. Our Earth cannot survive without the greenhouse gases. So what role do they play in our planet's existence?
Yeah, it's a great question. I mean, if you think about the word itself, greenhouse gas, it's come to have a negative connotation. But if you think about a greenhouse, that's a beautiful thing, right? You're growing these flowers and these fruits, and it's warm. Greenhouse gas is responsible for life on Earth. It keeps us warm. It's the blanket that we have, which would otherwise be a very cold night. And it also is the carbon source that nature uses to grow. So when a tree grows, it's pulling greenhouse gas out of the air and using that as the building block to make everything that you see, the leaves, the bark, everything. Greenhouse gas is really the fundamental starting point for most of life. The problem is we're putting too much of it into the air.
So how does it create a blanket? Could you explain that a little bit more to our listeners who don't think about these things every day like you do?
When we talk about greenhouse gas, what it really means is heat trapping gas. And so if you think of the Earth like a big ball, around the Earth, there's a layer, and that's effectively our air. So as that air fills up with more heat trapping gas, what happens is as the warmth of the sun hits the Earth, when you have heat trapping gas, it holds that heat in the air around us and doesn't allow it to escape. So you can kind of think of it like the more blankets you put on, right? You keep getting warmer and warmer and warmer. Well, that blanket's great to a certain degree, but too many blankets and you get too hot. And so that's effectively what's happening. As we're putting in more heat trapping gas into the air, it's effectively heating up the globe.
And you mentioned that right now, carbon dioxide, which is probably the largest component of greenhouse gases in our atmosphere, it's about 400 parts per million. How much was it, say, a couple of centuries ago?
One of the reference points that people turn to is 350 ppm. And the idea is if we could somehow stop the accumulation of carbon and then reverse it back to 350, there would be some level of normalization. Whether we can achieve that is a different question, but I don't know specifically what it was 2 centuries ago, but I think within a relatively short history, it was only as low as or as close as 350 ppm. And so you can see how important just 50 or 100 ppm of this gas is in the air. It makes a huge difference in terms of the climate.
So we have carbon dioxide, we have methane, we have nitrous oxide and fluorinated gases, which are kind of the largest, the biggest 4 greenhouse gases that are there. But how their parts per million increases is different, right? So carbon dioxide is because of how we burn our fossil fuel, maybe cement construction. What contributes to, say, the increase in methane or nitrous oxide or fluorinated gases?
Most of it is industrial activity, but in the case of methane, the biggest sources include landfills. So the more trash that we have and the more it goes into these, landfill, you might call them dumps, they effectively ferment and they create carbon dioxide and methane. Some of that methane gets into the air. So that's one big source. Another really big source of methane is just from the production of meat and dairy products. So dairy cows burp about 600 liters of methane per cow per day. It's quite a bit. And so next to landfills, you have just agricultural operations as a very, very large source. I think it used to be around 20% of all methane emissions came from cattle operations. Where you get sort of these compounded effects is when you cut down a rainforest and use it to graze cattle, you're not only releasing all the CO2 from that was locked into these trees and these forests, but then you're putting cows on them that are burping out methane. Other sources include energy operations, things like natural gas, oil drilling, transmission lines. You have old abandoned coal mines that can be a source where they just continue to flow methane into the air. Those are some of your biggest sources.
Is there something which can absorb methane, like carbon dioxide? If it's let out, trees can absorb it. But what about methane? Is there anything that could mitigate it, reduce it?
Well, that's a great question. It turns out that there are microorganisms in the environment that naturally eat methane as their food source. In fact, during the BP oil spill about a decade ago, whenever it was, there was an article in National Geographic that talked about how all this methane was pluming from these leaks in the ocean. And for some reason, a big portion of that was not making its way to the ocean surface. They asked the question, well, where did all this methane go? And as they looked at it, they discovered that there are microorganisms in the ocean water, naturally occurring microorganisms, and their food source is methane. So as this stuff was bubbling through the salt water, they were eating it as their food source and just making more of themselves, kind of like plankton or algae. And so it turns out that these microorganisms exist in all kinds of places, from the ocean to estuaries. Frankly, anywhere that you have even very small amounts of methane, you can find these microorganisms. So that's one example of how nature does actually take some of that methane back in.
That's pretty incredible. I never heard about how nature can correct some of the mistakes that mankind or humankind makes.
Well, nature has this really interesting philosophy, and that is that there is something of value in everything. And that's the basic premise of nature. CO2 as an example. As you mentioned, nature eats CO2. It's valuable. Methane's the same thing. Whatever it is, nature will find a way to turn it into something useful. Even a rock becomes shelter and shade for something. So if you look hard enough in the natural world, you'll find some system using something for good. And I think that's actually a really interesting and encouraging thought.
You hit the nail right on the head. Nature is our best teacher. It's had millions, if not billions of years to perfect so many of the things that we are still discovering, still inventing, in our mind inventing, but actually discovering. What does your product do? What is your invention? Firstly, did you invent this?
Well, we like to think we're just copying what nature does. Of course, we have many, many patents, so I suppose there is some level of invention there. But many years ago, back in 2003, we came across the issue of methane emissions. And at the time, everybody was talking about whether it was methane or carbon dioxide. For carbon, we should either be taxing this or burying it. both of those have a problem, which is they cost money. And so a lot of people just don't want to do that. Whether that's right or wrong, the reality is for decades now, we've been talking about carbon emissions. And unfortunately, not a lot has happened. There's certainly not as much as we need to have happen. And so we said, what if there was another way of looking at this? Nature takes stuff and uses it as a valuable resource. What if we do the same thing? So we early on realized that there were these microorganisms that do eat methane. And we also realized that when they grow, at least some of them make this material inside of their cells. And this material is called PHB. Most people don't know about PHB, but we're all making it in our bodies right now. In fact, almost all known life makes this molecule. And it turns out that you can feed methane or carbon dioxide to a microorganism, a natural microorganism. It'll eat that as a food source, and part of what it'll make inside of its cell is PHB. Well, if you extract that, it turns out that it's meltable. And because it's meltable, now you can use it to make different shapes and parts and pieces. But the big difference is, well, there's two. Number one, because this material is made throughout nature, it is a environmentally degradable material. Nature sees it as a banana peel or a fruit or a tree leaf, and so it can reconsume it. The second thing is, when that process happens in nature, the process that we described happening in the ocean, that's a carbon negative process. Effectively, when that process happens, there's less carbon in the environment than there was prior to the process happening. So that got us really excited. We said, well, hold on a second. Nature already has a pathway where it's taking carbon, using it as a valuable resource to make something that not only can we reduce the amount of carbon in the air, we can also potentially displace synthetic plastic that doesn't go away with a natural material that does. So that was really compelling to us.
How is this PHP molecule, how does that compare to a polymer molecule?
Many things are polymers. So your hair is a polymer. Many parts of a tree are polymers. Many natural materials are polymers. So I think, but in terms of synthetic polymers and specifically plastics, how does PHB compare to that? The first big difference is that PHB or AirCarbon is made biologically as opposed to synthetically. So microorganisms produce this, human body produces this, everything alive pretty much makes this material. Whereas with a plastic, that's in a test tube. So you're taking a catalyst and you're taking ingredients, oftentimes very dangerous ingredients, and you're carrying out a reaction that does not occur in nature by itself. So here you have a naturally occurring process versus a synthetic process. The reason why that's so important is because when that synthetic material ends up in nature, nature doesn't know what to do with it. It doesn't have the tools and the resources to break it down like a food source, like it would with a banana peel. In contrast, PHB, it does have those tools.
Even if the plastic is made out of a plant, they have these bioplastics now because technically you can make polymers out of plants too. So even that is disruptive to nature's plan, according to you.
This is such a good point that you raise. Just because something originates from plants doesn't necessarily make it good. You can have something that has way more carbon emissions, and you can have something that is a synthetic material that nature doesn't understand. So sure, you can start with plant-based material, but if you're using it to make the exact same molecule that comprise traditional plastics, that same bottle is still not going to go away when it floats in the ocean. What's really important in our view is making the actual material itself through the same pathways that happen in nature with the same molecule that exists in nature. If you do that, then nature understands it and it's not disruptive.
So you seem to know a lot about chemistry and biomimicry. I'm not sure what field of science exactly your research would fall in. Do you have a science background? Is your degree in these areas? Which field would specifically your invention belong to?
I think microbiology is the first sort of core part of our technology. The second is material science. So kind of the different stages that we go through in our manufacturing. First thing we do is find those microorganisms. Second thing we do is figure out how to grow them in a way from greenhouse gas that makes them happy and they make this material. Then we have to extract that. And once we've extracted it and dried it, it turns into a fine white powder. We melt that. And then we need to figure out how to process it, how to make a fork or a wallet. And that's material science. And so those are kind of the biggest areas for us. On a personal level, I've now been doing this for about 19 years, so I've been exposed to a lot. My college degree was actually in political science. But the reason that I got into political science was because in high school, I was, I guess you can say the word pretty nerdy. I was on every science class that I could. I was on the National Oceanographic Science Bowl team, where they had this panel of people and they'd ask you questions and you'd buzz in and say dinoflagellate. And so I did so much science in high school that when I got to college, I was really interested in looking at philosophy and religion and kind of the other side of things. I ended up getting very sick. And in my quest to figure out what was going on with me, I decided that I was going to go and do a post-bac and go to medical school. So science has always been a really important part of my life. And then after we started Newlight, a lot of the work was kind of ground up. And so we had to learn how bioreactors and microorganisms work, how you could get different conditions and cause them to behave in different ways. It took about 10 years to figure out how to mimic what was happening in the environment and do that, on land.
So you have a co-founder. What role does he play in your organization, in Newlight?
So Kenton studied biomedical engineering at Northwestern, so brings a great additional science eye to what we do. But as importantly, he's just been a really trusted partner. My mom was actually his 4th grade teacher, and then we met in 6th grade. And so we've known each other for most of our lives. I think that was really important in the early parts of the company because we had seen each other grow up in middle school and high school. And so there was a certain inbuilt trust for the kind of person that you were working with. It's been a really important partnership in developing the technology and working through ideas and challenges as they come up. He's our chief technology officer, focuses on right now primarily the expansion of our production capacity. So we're building a new plant now, and he's really focused in that area.
So you said it took 10 years to kind of bring your idea to market. How did you fund yourself those 10 years?
At first, it was odd jobs. I was a bellhop in the morning, and then I was a fitness attendant in the afternoon, and then would drive out to our laboratory. Kenton was a valet, and after about a year and a half of that, we were able to raise our first round of capital. We raised $1.8 million, and with that, we were able to build our first pilot facility. And we spent about 10 years going from lab scale to pilot scale, and then finally small commercial scale. So it started pretty scrappy, and then friends and family, and then that progressively got more and more institutionalized as we kept having additional proof points in our technology development.
So talk about the technology. What exactly happens in your now pilot plant? I would encourage our listeners to go and take a look at their new plant. It looks really cool. It looks out of this world. Maybe a little bit like a beer plant, if people have seen it. Is it? I don't know.
We should start an AirCarbon beer. Well, I appreciate you saying that because for me, it is definitely one of the most beautiful, and I've said this before, but I think it's one of the most beautiful things that I can look at because, well, a couple reasons. Number one, 18 years ago, we were dreaming about this facility. And I remember sketching it on a little yellow notepad, and it was so far away, and we had no idea how far away it was. But to see it now in reality it's really special. But the second thing is what it represents. And what it represents is not just a natural technology at work, but also hopefully the beginning of a new way of making materials where we don't use synthetic pathways, we use nature-based pathways. And so the way that it works is, in the most basic terms, is we start with a big tank, and that's about 10 feet wide, about 50 feet tall. And you can kind of think of it like a slice of the ocean because we basically fill that tank up with salt water. And into that saltwater solution, we add these naturally occurring microorganisms. And to that, we then feed air and greenhouse gas. Those gases bubble up through the salt water. And as they do that, the microorganisms eat those gases as their food source. By weight, AirCarbon is about 40% oxygen from air and about 60% carbon and hydrogen from greenhouse gas. And so they fill their cells up with this material, kind of like building muscle. And then we take that out and we put them through a high pressure filter, and that isolates the AirCarbon polymer that we've made. And then we dry that into a fine white powder. And then with that powder, we can melt that into pellets. And once we have the pellets, we can use those to make all kinds of parts and pieces. So at our current facility, we're making everything from straws and cutlery. We also make a replacement for leather. So we'll make sheet and then send that to somewhere else to have them stitch that into various parts and pieces. And we're also making things like eyewear. So we'll send those pellets over to Italy where they're formed into eyewear and then shipped around the world.
And these products that you create now, they are biodegradable or compostable? Because we have commercial and or residential biodegradable products, and then we have compostable products.
The problem with the industry right now is it's confusing for the whole industry is confused. And the reason is right now, there are a lot of products that are labeled quote unquote compostable. What does that mean? So right now, the laws are mostly written is that you can call something compostable, but it doesn't necessarily compost in your backyard or in other normal natural environments. Usually compostable today means it has to go to a very, very hot compost. And there are very few of those. But if it ends up in nature, it won't go away at any different pace than normal plastic. So the term biodegradable is thought to be somewhat interchangeable, and there's a ton of legislation around this. As an example, in California, you can't call anything biodegradable. Nothing. It doesn't matter if it's a glass of milk. Like, nothing's allowed to be called biodegradable.
Even a leaf is not biodegradable.
Nope, nothing. So in California, you can say either compostable or home compostable. Now, home compostable is the harder standard. And in order to pass that, you have to demonstrate that in a home compost condition, this product will go away. So there's a ton of tests around this. And I think the industry is still maturing to try to get to really standardized stuff that, number one, is standardized, but number two, makes sense to consumers. It's kind of like when you go to the airport, right? And you get to that moment where you see the 3 or 4 trash bins, and there's trash and landfill and recycle and compost. And you're thinking to yourself, I really want to help. I do, but I don't know where this goes. And that's part of the problem is there's too much confusion. So that's a big task for the industry, is to kind of clean all that up and make it simple for people.
So your product is biodegradable or compostable?
Our material is something that exists in nature, so it's biologically degradable. When for instance, our straws are home compostable. They're also commercially and industrially compostable. There used to be standards to claim ocean degradability, and we passed those as well for that product. So this material is as degradable as any other natural material, and then we just have to follow whatever letter of the law it is, but it's about as good as it gets.
What is surprising is that your products are also dishwasher safe. So they can tolerate this high heat, high pressure, drying, and hot water soap and still retain the integrity of usage and shape.
Yeah, I'm going to nerd out here for a second, and I'll tell you why that happens. Because people ask, how can something be home compostable, but then dishwasher safe? Like, doesn't the water break it down? So this molecule was called hydrolytically stable. So water doesn't do much to it. So water just runs off it. The way it's consumed is enzymatically. In other words, microorganisms have to eat it. So how does dishwasher safe play into this? The reason why nature makes this is because it's an energy storage material. So our microorganisms make it because they're in conditions where they want to store this material up as sort of a protective safety mechanism. Why that matters is to get the biggest packing density possible, it becomes a very crystalline material. Okay, so what? Well, at high crystallinity, that means you have to put a whole bunch of temperature into it in order for it to do something different. So because our material is so high crystallinity, is able to withstand high temperatures, so boiling water, dishwasher conditions, all of that. However, if it ends up in the soil and something starts chewing on it, it can chew on it just fine. So it has this really interesting combination of water doesn't touch it, it's dishwasher safe, but it will go away in these environmental conditions. That's just lucky. We didn't design that. That's just how nature made it.
How would you compare your material to bacterial cellulose?
Very comparable, actually. This is a component of microorganisms. This is one of the things that they make as a way to thrive and to stay alive. But again, this is made throughout nature. Animals, trees, grass, it's made all over. So cellulose tends to be a stacked material. This is a polymeric material. Now cellulose is as well, but it functions differently. It's a molecule that's easier to access. So microorganisms can chew it up faster. For instance, there was an old ocean degradability test, and I'll bore you with the number real quick. It's ASTM D6691 for anybody who wants to look it up.
I saw that on your website. What is that?
It's kind of like ISO systems, but ASTM is a test-making body that gives prescribed tests, and so everyone follows the same thing. So there used to be a test for ocean degradability called 6691, and there was 7081 as well. And the way that you passed that test in order to say something was ocean degradable was you had to degrade in ocean water faster than cellulose. And in fact, when we ran our test, there's three things you put in. Normal plastic doesn't go away at all. Cellulose, which does go away, and then whatever material you're testing. We showed that our material, actually the Chico Research Foundation showed that our material went away faster than cellulose because it was easier for microorganisms to consume.
So Newlight is using blockchain. What exactly are you doing? Usually blockchain is for transparency, traceability. So how does it fit with your invention, your process, your material?
Yeah, and that's exactly why we're using it as well. We have these two features, degradability and carbon negativity. If you take one of our straws as an example, you can put it in your fish tank and you can watch it, it'll go away. So you can verify that. With carbon negativity, on the other hand, it's harder to verify what we're saying. And so we reached out to IBM a few years ago and we said, can you help us set up a blockchain tracking system so that we can track all of our carbon inputs and outputs, so that we can help walk people through the carbon story and make sure that it can be easily and quickly validated. So we did that. It took about 2 years to set up. Today, we have our lifestyle products, our eyewear, our wallets or whatever. They come with a blockchain number. And the idea is, and you can do this, that number is individual to the product, and you can type it into our website, and then it'll show you every step in the production process. But perhaps most importantly, it'll show what the specific carbon footprint is of that product, as well as who independently verified and calculated that number. So that was a way to give people the ability to really deeply understand the carbon footprint and impact of that product. So we thought it was a really interesting application of blockchain technology.
How is that different from RFID chip in a Starbucks reusable cup?
The big difference is with blockchain, you can't change the data. So once it's in there, it can't be moved, it can't be changed. And so it has that deep verifiability, which is why it's used in crypto and all these other things. And so our data flows directly onto the blockchain and gives the ability to verify the carbon footprint of what we're doing. Whereas RFID technically just tells you information, but it doesn't have any mechanism to ensure that that information hasn't been changed or manipulated in any way.
So where can somebody buy your products? Are you just a supplier of raw materials for finished goods, like somebody who wants to make cutlery or shoes? Where can somebody buy your products?
We're carried in a number of locations now. So on the foodwear side, the easiest way is to go to target.com. They're carried, you can search for AirCarbon or Restore is the current brand name. And so right now we have straws and cutlery. We're about to roll out a bunch of other products as well. And then we also have our lifestyle products. So every day I wear my AirCarbon eyewear. Obviously I'm a little bit biased, but I think they're fantastic. And then we also have leather replacement items. So my wallet is made with AirCarbon. We're rolling out things like bags and other items. And that's on, if you go to Newlight, you can find all this stuff, newlight.com, but target.com has our foodwear. And then the fashion products are carried at covalentfashion.com. And yeah, it's fun. I mean, I still get joy out of this idea that 18, 19 years ago was just this crazy idea. Now today I can go online with a few clicks of the button. I can get products made from greenhouse gas, made by trillions of microorganisms. I think that's pretty cool.
How tough is this material? Because if you think about our cars, so many of the parts are made out of plastic. And is your product, is AirCarbon tough enough to be made into a bumper?
The short answer is yeah. Our biggest challenge is these markets are so big and our production capacity is so small compared to those markets. So we kind of have to pick and choose where we play. But we are working in automotive. We actually just signed a deal with an automotive partner a few weeks ago. It's a tough material. If you buy our cutlery as an example and you look at one of our forks, it's not flimsy. It's not one of those annoying forks that you can barely, poke your lettuce. It's not breaking. It's just a really tough material. It does have the ability to work well in things like automotive, but we're in a number of segments from foodwear to lifestyle to automotive. And one of our tasks is to say, okay, we have limited capacity right now, and we're going to be supply limited for a long time. Where can we have the most impact? And so we looked at what's happening in the oceans. And basically the oceans are filling up with two things, fishing equipment and foodwear. And so we said, let's start by using AirCarbon to address the foodwares market because we think we can have a major, major impact there. And our goal is to eventually make 20 billion pounds per year of material. That's the amount of plastic currently flowing into the ocean every year. and show that this problem doesn't have to keep happening. I mean, no illusions about how hard it's going to be to stop it. There's going to have to be a lot of efforts, but we don't have to keep making these products out of plastic that doesn't go away. We can use nature-based materials, and that's our goal.
When was your plant set up?
I guess many plants over the years, but our first commercial scale plant started delivering products to the market for the first time in Q4 of 2020.
What has your impact thus far been towards your goal of 20 billion pounds of reducing plastic that goes into the ocean?
We've got a long ways to go. Over the past year, we've been delivering millions and millions of products to people. And I think of those, if you think of like one straw as an example, yes, I get it. It's just one straw. But on the other hand, that's one opportunity out in the environment somewhere for something bad to have happened. These are all individual experiences. Look, we're very small compared to where we want to be, but there's so much interest in this material because of what it does. And we believe it has all the ingredients to create real scale. So it's going to take time. It's not going to be easy, but we really believe in what's possible with this technology.
On that inspirational note, thank you so much, Mark, for coming on Mindful Businesses.
Thank you so much for having me.
You're listening to Mindful Businesses, hosted and produced by Vidya Iyer. We'd love to hear from you. Send us a voice note with your questions or comments to info@mindfulbusinessespodcast.com. Subscribe, rate, and review us on Apple Podcast. If you learned a thing or two from this episode, share it with one friend. We recorded this podcast in Lafayette, Indiana. Theme music composed by Tatum Gale. Our marketing assistant is Caitlin Milligan. Our advisors are Jim Stone and Anupama Bustrija. This is Vidya Iyer with Mindful Businesses.